Welcome to this presentation on electronics. Electronics is the study of how electrical circuits can be used to control and process signals. In this topic, we will explore components such as diodes, transistors, and logic gates, and understand how they are used in modern devices. Overview of the A-Level Electronics option. The electronics option builds directly on the core electricity and materials topics and focuses on how physical principles are applied in modern electronic systems. This option is designed to show how relatively simple components can be combined to create complex analog, digital, and communication systems. The specification is divided into discrete semiconductor devices, analog and digital signals, analog signal processing, digital signal processing, and data communications. Each section introduces real-world devices such as MOSFETs, Zener diodes, photodiodes, operational amplifiers, logic gates, counters, and communication links. Semiconductors, doping, and charge carriers, MOSFET structure and switching behavior, Zener diodes and voltage reference circuits. Semiconductors form the foundation of all modern electronics and are characterized by a small energy band gap between the valence and conduction bands. In intrinsic, pure, semiconductors such as silicon, thermal energy at room temperature excites a small number of electrons into the conduction band, leaving behind holes in the valence band. Both electrons and holes act as charge carriers and contribute to conduction. The electrical properties of semiconductors are dramatically altered by doping, which involves adding small amounts of impurity atoms. N-type semiconductors are produced by doping with group 5 elements such as phosphorus, which donate extra electrons and make electrons the majority carriers. P-type semiconductors are doped with group 3 elements such as boron, creating additional holes that act as the majority carriers. The distinction between majority and minority carriers is crucial for understanding devices such as diodes, transistors, and photodiodes. Unlike metals, the conductivity of semiconductors increases significantly with temperature because the number of charge carriers rises rapidly as more electrons cross the band gap. This temperature dependence explains the behavior of components such as thermistors and must be contrasted with metals, where increased lattice vibrations increase resistance. The metal oxide semiconductor field effect transistor, MOSFET, has the N-channel enhancement mode MOSFET. A MOSFET has 3 terminals: gate, source, and drain. The gate is separated from the semiconductor channel by a thin insulating oxide layer, giving the device an extremely high input resistance. When the gate source voltage is below the threshold voltage, no conducting channel exists and the MOSFET is effectively switched off. When the gate source voltage exceeds the threshold voltage, electrons are attracted to the region beneath the gate, forming a conducting channel that allows current to flow from drain to source. This makes the MOSFET an efficient electronic switch that can be controlled by a very small input current. A Zener diode is a specially designed p-n junction diode that operates in reverse bias at a well-defined breakdown voltage known as the Zener voltage. Unlike ordinary diodes, which are damaged by breakdown, Zener diodes are manufactured to exploit this effect safely. When the reverse voltage reaches the Zener voltage, the diode conducts while maintaining an approximately constant voltage across it, provided a minimum operating current is maintained. Zener diodes are commonly used with a series resistor to form a simple constant voltage source or reference voltage. Analysis of such circuits involves applying Kirchhoff's laws to calculate currents and voltages. Photodiodes and optical detection, Hall effect sensors, and magnetic field measurement. Photodiodes are semiconductor devices designed to detect light and convert it into an electrical signal. Photodiodes are considered in photoconductive mode, where they are reverse biased so that incident photons increase the current through the device. When light of sufficient energy strikes the depletion region, electron-hole pairs are created, increasing the photocurrent. The magnitude of this current depends on the intensity and wavelength of the incident radiation. Photodiodes have important applications in optical communication systems, light meters, and safety devices. Hall effect sensors are used to detect magnetic fields. When a current flows through a conductor or semiconductor placed in a magnetic field, a transverse voltage is produced due to the deflection of charge carriers by the magnetic force. In Hall effect sensors, this voltage is measured and related to the strength of the magnetic field. For example, a rotating magnet passing a Hall sensor produces pulses that can be counted to determine rotational speed. These applications demonstrate how electronic sensors interface with mechanical systems and produce signals suitable for digital processing. Analog versus digital signals and noise, analog to digital conversion, and sampling. Analog signals vary continuously with time and can take any value within a range, while digital signals use discrete levels, typically represented by binary values. In electronics, many sensors produce analog signals that must be transmitted or processed. However, analog signals are particularly susceptible to noise, which can distort the signal during transmission. Digital signals, by contrast, are more robust because small amounts of noise are less likely to cause errors if the signal levels remain distinguishable. Analog to digital conversion, ADC, is the process of converting a continuously varying analog signal into digital data. Sampling involves measuring the analog signal at regular time intervals, known as the sampling rate. Quantization involves rounding the sampled values to the nearest available digital level, determined by the number of bits per sample. Increasing the sampling rate and the number of bits improves the quality of the digital representation but also increases data size. Graphical representations of analog signals and sampled data are commonly tested, including the effects of insufficient sampling leading to loss of information. LC resonance filters and frequency response. LC resonance circuits are used as frequency-selective filters. Only parallel LC circuits are required. At the resonant frequency, energy oscillates between the capacitor's electric field and the inductor's magnetic field, producing a peak in the voltage response. Bandwidth is defined as the range of frequencies over which the energy is greater than half its maximum value. The quality factor Q is defined as the resonant frequency divided by the bandwidth and provides a measure of how selective the filter is. Interpreting frequency response curves is a key exam skill. The specification also introduces an analogy between LC circuits and mass spring systems. Operational amplifiers and their applications, digital logic, processing, and data communications. Operational amplifiers, or op-amps, are high-gain voltage amplifiers used extensively in analog electronics. These assumptions simplify circuit analysis and are used to derive relationships in common configurations such as inverting and non-inverting amplifiers and comparators. Op-amps are used to amplify weak sensor signals, compare voltages, and perform signal conditioning before analog-to-digital conversion. Digital signal processing and data communications focus on the operation of basic logic gates such as AND, OR, NOT, and NAND, which can be combined to form counters, registers, and timing circuits that process digital data. Data communication concepts include the transmission of information using electrical, optical, or radio signals, and the use of techniques such as modulation and multiplexing to improve efficiency. In this topic, we have explored how electronic components work together to control signals and devices. Understanding resistors, sensors, diodes, transistors, and logic gates allows us to analyze and design useful electronic systems. Thank you for watching.